Okay, before we get into the key idea of the chapter, and actually the whole course, I want to talk about some notation you need to know. Some of you might already know this. Sigma notation or summation notation. The idea is when you say you're adding up a bunch of numbers like this, it can be written more compactly as the sum I equals 1 to 6 of I. Think of it like a for next loop. I starts out to be 1, and so you have 1 added to, now I is 2, and then added to, now I kicks up to 3, so you keep going until you get up to the top index. So in other words, it's a for next loop. Sum equals sum plus I for I equals 1 to 6, right? Anyway, so for example, when you see the sum k equals 2 to 4, k squared, k starts out to be 2, you get 2 squared plus, kick this up 1, k is 3, so now you get 3 squared plus, and the last one would be 4 squared. So we're going to use that a lot, and also you'll use it in Math 153. Alright, so let's look at this one. Well, what would the sum I equals 0 to 5 be of the expression I plus 1? Well, I equals 0, so the first term is going to be 1. I should say I plus 1, so when I is 0, you get 0 plus 1, so there's the first term. Now I kicks up to be 1, so the second term is 2, and so on. The last term, when I is 5, you get 5 plus 1, which is 6. Well, what I want you to realize is this sum is exactly the same sum we had in problem number 1. So the point is there may be lots of ways to write the same sum using this notation. You just might have to write a couple terms out to see what's going on. This is kind of nice. Look at this. I equals 1 to 4 of 3. So when I equals 1, you get 3. You're adding it. Now I is 2 to 3. See how this stays the same each time? So the last one is I equals 4. And you still are adding 3 to itself. So that's a fancy way of writing 12, isn't it? Let's look at this one. The sum I equals 1 to n of I cubed. Now n would be a positive integer. You don't know what n is, so the way you'd write it is like this. You'd write I equals 1, so you get 1 cubed plus, now I kicks up to 2, you get 2 cubed, and then the last one would be n cubed. This one right here, j equals 1 to n of 3 over j. J is 1, so the first term would be 3 over 1. Added to, when j is 2, you get 3 over 2, so on. All the way up to the last term, when j equals n, it'll be 3 over n. See it? Alright, now especially in Math 153, you're going to encounter this. You see this negative 1 to the k business? Well, what that does is it alternates. You see, whenever k is an even integer, this is going to be a positive 1. Whenever k is an odd integer, negative 1 to an odd power is negative 1. So what this does is it alternates the terms. So when k equals 1, you have negative 1 to the 1, which is negative 1 times 2. The first term is negative. Plus, when k is 2 now, this negative 1 to the 2 is a positive, so it alternates the sign. You'll see that a lot in 153. The last term, depends if n is even or odd, doesn't it? But either way, the last term will be negative 1 to the m times 2 to the m. Alright, see if you can do this one. See if you can figure out what this actually equals. The sum I equals 0 to n of 1. Hit the pause button. So you get this. Now my question, is this equal to n? The answer is no. It equals n plus 1. You see, because you start at 0, you actually have n plus 1 of these 1's added together. So that was sneaky, wasn't it? Alright, let's do a couple more things here. By the way, this is all in the Appendix E. In back of your book, you'll see Appendix E. You can review this if you want to go over more depth. But there are some properties of some summations that should make total sense, I think, because remember that this is just the sum I equals 1 to n. Actually, it's actually I equals m to n. Doesn't even have to start at 1, does it? Of c times a sub I. You can factor the constant out. As long as c doesn't have any I in it, it's just a constant. This is just the distributive law, isn't it? Written in summation notation. Similarly, if you have a summation of a sum of expressions, you can clearly break it up into the sum of each of them. These are easy to prove. We're not going to prove them though. Same is true with a difference. If you have a summation of a difference of two expressions, you could break it up and say it's the summation of the first minus the summation of the second. So for example, look at this one. The sum I equals 1 to n of 5 over x to the I. You could move the 5 out of the summation sign, so it becomes 5 times the sum I equals 1 to n of 1 over x to the I. Similarly, if you got something like this, sum I equals 1 to n of 3i plus I squared, you could break it up like this. You see, you could move the 3 out of the first one. First of all, you could break it up into 2, then you could move the 3 out of the first one. We're going to be doing this in just a little while in this class. Anyway, so these properties can be summarized. This is the one we talked about here. Sum I equals 1 to n of 1 is n, as long as you start at 1, right? The sum I equals 1 to n of c, you're adding c to itself n times, that's just n times c. Now these last three are really important. They're kind of messy. In my class, I'm not going to make you memorize these, but look at what they say. This first one says that if you're adding the sum I equals 1 to n of I, so for example, let's say we have I equals 1 to 10 of I. That would be 1 plus 2 plus 3 plus 4 all the way up to 10. What it says is there's a formula that will always give you the sum. So it will be, in this case, 10 times 11 over 2. So it'll be 55, you see? That's a nice little formula for adding up the sum. Look at what D says. D says the same idea. If you're adding I equals 1 to, say, 10 of I squared, there's a nice little formula that will always give you what the sum is. In this case, it would be, if n equals 10, it would be 10 times 11 times 21, I guess, all over 6. And so if you were to reduce that, I think you get 385. You can check me on that. I think this is kind of an interesting formula. What it says is no matter how many you add together, if you add the squares of integers up, it'll always be divisible by 6. I think that's kind of interesting. It even works when I equals 2. Look, when I equals 1 to 2 of I squared, you get, the formula says it equals n, which is 2, times n plus 1, which is 3, times 2n plus 1, which would be 5, and divide by 6. So the 6's cancel, and you get 5. So I think that's cool. Anyway, amazing, isn't it? Let's see. So these last three formulas you can use. They will come up. But I said in my class I'd probably give you these on a quiz or test, but these will occur. So let's look at some examples of these. So how would you express this in terms of n? Well, first of all, you could use our properties, and you could break this up into 5 times the sum I equals 1 to n of I, plus 3 times the sum I equals 1 to n of 1. Now what is the sum I equals 1 to n of I? The formula says it's equal to n times n plus 1 over 2, so you get this expression. You could actually simplify it a little bit more if you wanted to, but this is good enough for now. All right, let's look at this last one here. Suppose I wanted to express this in terms of n. In other words, what we're doing, folks, is we're getting rid of the summation sign, right? Okay, we could first of all use our properties and break this up into the sum of each of them. Take the 2 out and the 3 out. Now the I squares, sum of the I squares is this one right here we just talked about. So you get here, you can replace the sum of the I squares with this expression, and then the sum of the i's is n times n plus 1 over 2. You can do that. Now remember, the sum of the I equals 1 to n of 1 is just n, so there you go. Alrighty, so we're going to use this notation in this chapter. So if you haven't seen it before, you might want to go and look at Appendix E in your book. Alright, we'll see you later. Bye-bye.